Hello everyone, this is Preetam from LinkedIn, and today I'm going to talk about fairness of exposure in rankings. Let me start with a motivating example. People you may know, or PYMK, is one of the main products at LinkedIn that serves millions of members every day. In this product, a viewer gets a recommended list of candidates to whom they can send connection invitations. The recipients of these invitations can then decide to accept those invitations to form connections. And the question we are asking here is whether or not the potential recipients of these invitations are getting exposed fairly, in the sense that if two potential recipients are equally qualified to receive a connection invitation, then they should get equal exposure. To quantify the fairness of exposure in ranking, we consider a score-based ranking systems where the candidates are ranked according to the scores given by a machine learning model. Among various definitions of fairness in the literature, we focus on equality of opportunity and equalized odds in this work. So this fairness metric consider the conditional independence of the exposure and the characteristic given the response. Since a candidate with a higher score always gets a higher exposure, the problem reduces to considering the conditional independence of the scores and the characteristic given the response. Now, equality of opportunity considers fairness for qualified candidates, which corresponds to positive responses, but equalized odds consider fairness for both qualified and unqualified candidates corresponding to positive and negative responses. Broadly speaking, there are three types of bias mitigation strategies: pre-processing, in-processing, and post-processing. In this work, we consider post-processing solutions, which changes model scores after training. This is a highly desirable property in large-scale industrial settings where we may not want to touch the current model training pipeline. Our main contributions are post-processing algorithms for achieving equality of opportunity and equalized odds in score-based recommender systems. Our algorithms can handle continuous prediction scores and the presence of position bias. The algorithms are scalable and model agnostic, and we provide an explicit parameter for fairness and performance trade-off. The main drawbacks of our algorithms are that they can be only applied to score-based rankings, and they can be less flexible than in-processing algorithms for trading off fairness and performance. Let's recall the definition of equality of opportunity that ensures the conditional independence of the score and the characteristic given positive responses. This is equivalent to the equality of the score distributions given the response equals 1 for all values of the characteristic C. Going back to the connection recommendation example, if we consider frequent and infrequent members as two groups for which we want to ensure fairness, then equality of opportunity will ensure that frequent members who has received invitations has the same score distribution as the infrequent members who has received invitations. Here we show that equality of opportunity can be achieved with group-specific score transformations. The main idea here relies on the fact that if we have a random variable x with a cumulative distribution function f, then the random variable fx has a uniform distribution. So what we do here is that we compute the cumulative distribution functions of scores for each group for which we have the positive responses and apply that function to all scores in that group. So we illustrate this with an example here where we denote the scores corresponding to negative labels with red circles, and we denote the scores correspond to positive labels with green triangles. On the left-hand side, we see that the score distributions of group C1 and group C2 are different for positive levels before the equality of opportunity transformation. And after the EOpp transformation, we see that the score distributions of the green triangles are uniform for both groups. And that means also we have the same distribution for both groups, but we cannot guarantee anything about the score distributions corresponding to the negative levels, which are depicted by the red circles. Finally, we demonstrate how fairness and performance trade-off can be controlled through an explicit parameter. For this, first we bring back the distribution of the transform score to the original scale. To do this, we consider F the CDF of the original scores and G the CDF of the transform score, and then we transform the transform score with F inverse G, and this guarantees that we have the same distribution of the transform score as the original distribution of the scores. So after this, we can just blend the transform score and the original score with a linear combination using a tuning parameter alpha. Basically, we consider 1 minus alpha times S plus alpha times the transform score, which is F inverse G of F star. And as we increase alpha to 1, we get 100% fairness guarantee. And as we decrease alpha to 0, we are back to the original scores. Yeah, so by changing alpha between 0 and 1, we can tune how much fairness we need, and that might also tune how much performance we are getting. Next, we consider equalized odds for score-based ranking. And equalized odds is same as the equality of opportunity and an additional constraint which guarantees the same distribution of scores for negative levels as well. Unlike equality of opportunity, there is no deterministic transformation that would give us equalized odds. We can solve this problem with some probabilistic transformation. So first, consider a simple classification problem where we are considering binary predictions instead of continuous prediction scores. Then we can achieve equalized odds by changing the prediction with some probability PYC. So basically, whenever we predict a positive level with probability P1C, we change it to a negative level. Whenever we predict a negative level, we change it to a positive level with probability P0C. And we can choose these probabilities so that the equalized odds constraint is satisfied. So in case of continuous prediction score, what we can do is that we first discretize the score into T beans. So you can choose the beans according to the score quantiles. And then we do a randomized allocation of the score. So for each score in bin BI, we can transform the score to bin BJ with probability, let's say PIJ. Okay. And then we can choose these probabilities Pij such that the equalized odds condition holds. So if we don't want strict equalized odds, then we can control the difference between probabilities for two different groups for each pin with a tuning parameter epsilon. So as epsilon goes to 0, we have strict equalized odds. And if epsilon is large, then we are not restricting ourselves to equalized odds. And there are multiple solutions that can achieve equalized odds, but we want to choose the best one according to the performance. For that, we formulate this as a linear program where our objective is to maximize model performance such that the equalized odds constraint holds. So you can think of maximizing model performance in various ways. One way could be that we kind of assume that our original scores has already achieved the maximal model performance, and we want to stay as close as possible to the original score. Then our objective could be that minimize the expected difference between the transform score and the original score. And based on that, we can choose the probabilities Pij, or you can have another objective function that is trying to maximize the AUC, ROC. And in this case, this becomes a quadratic problem instead of a linear program. In the simulation setup, we generate data with position bias and apply EOpp and EOS transformation that can correct for position bias. On the top panel, we see that we have the score distributions corresponding to the negative levels. And after EOpp transformation, we could not achieve a match in the distribution, which is expected as EOpp is not considering the negative levels. But after EOS transformation, we do see a match in the score distribution for negative levels. While for positive levels, we do see a match in the score distribution for both EOpp and EOS after the transformation. Finally, we consider the fairness and performance trade-off with the tuning parameter alpha, as I mentioned before. And as you see that as alpha increases to 1, the distance between the distribution goes down to 0, except for the case the negative levels and when we are considering EOpp. And on the right-hand side, we see on the x-axis, we have alpha, and on the y-axis, we have performance, which is measured through the positive response proportion, because the model is trying to maximize the positive response. And surprisingly, we see that as alpha increases, the performance also increases for EOpp. So this can happen in the case where the underexposed group is actually the better performing group, and through achieving EOpp, we overexpose the better performing group, and then as a result, we get better performance as well. We see a similar trend in the real world experiments on LinkedIn connection recommendation systems, where we apply EOpp and EOPS to infrequent members and frequent members group. And after applying both EOpp and EOS, we see that we see a lift in the performance in terms of the number of invitation sends and number of invitation accepted. And also we achieve EOpp and EOS. So this is happening because the scores of the infrequent members tend to be much lower than the frequent members because of their underrepresentation in the historical data. But after achieving fairness through EOpp and EOPS, we kind of equally expose the qualified infrequent and frequent members. And after that, we see an improvement in the metrics. In conclusion, we show that EOpp and EOS can be achieved through post-processing, and surprisingly, sometimes without sacrificing performance at all. Thank you.